Hello everybody, let's discuss removable, jump, and infinite discontinuities. In this first slide, I'd like to discuss the idea of what we call a removable discontinuity as one of the three types of discontinuities that we're discussing here. In a removable discontinuity, we call it removable because the limit exists, but the value of the function at x equals c is either different than the limit or just simply not defined. In this example, we're going to discuss the continuity of the function at x equals 2. So if we consider the function f of x equals x plus 2 when x is less than 2, f of x equals 5 whenever x equals 2, and f of x equals 2x when x is greater than 2, we can see that's what we're talking about here. Specifically, the function is definitely defined at x equals 2, because f of 2 is 5, as defined by the middle piece here. But when we look at the limit as x approaches 2 of f of x, we're going to get a different value. Specifically, let's look at what happens to the left and the right. On the left-hand side of this function, if we could take the limit when x approaches 2 from the left of f of x, we're dealing with the function x plus 2. And as x approaches 2 from that vantage point, we're going to get 2 plus 2, that is 4. But from the right, if we take the limit as x approaches 2 from values that are greater than 2 or slightly greater than 2, we're dealing with the function 2x. Again, that gets to 4. So our limit as x approaches 2 of f of x is equal to 2. Pardon me, is equal to 4. In this kind of discontinuity, we don't meet the third condition that the value of f of 2 does not meet the limit as x approaches 2 of f of x, and so we say the function is not continuous. However, it seems to be this kind that I'm pointing to in the picture up here. We call it a removable discontinuity because at this particular point, the value of the function is different than the value of the limit, yet the limit exists. All right, so we call that a removable discontinuity. We define a function to have a jump discontinuity to be the kind of discontinuity that happens when you have a two-sided limit that does not exist, because while the function may be defined at a certain point, the value from the left and the value from the right in the limit does not agree. Here's an example of that. In this case, we look at the function f of x equals 1/2 x plus 1, and we see that if we take its limit as x approaches 2 from the left, we're dealing with the function 1/2 x plus 1. Letting x approach 2 gives us 1 plus 1 gives us 2. Yet if we take the limit as x approaches 2 from the right of the function 3 minus x, because we're approaching from values that are greater than 2, we find that we get 3 minus 2, which is 1. Since these two don't agree and they go to two different values, our limit as x approaches 2 of f of x does not exist, and we say that we have a jump, as illustrated in the graph, a jump discontinuity. Finally, the last kind of discontinuity that we discuss is called an infinite discontinuity, and we define it this way. It's going to be a discontinuity for which the two-sided limit as x approaches c does not exist, but this time, because the limit from the left or the right both grows without bounds towards positive or negative infinity. In other words, if you remember anything about rational functions, we're talking about the location of a vertical asymptote. But to illustrate the point here, let's talk about the function f of x equals x minus 1 over x squared plus x minus 2. If we rewrite this function before we even begin, we can see that the function could be rewritten as x minus 1 divided by x let's see, x plus 2 and x minus 1. And if we look at what's going to happen at x equals negative 2, we're going to see that this is not going to exist, because even though we cancel the common factor of x minus 1, we're still only concerned with what happens to this limit as x approaches 2, right? So x plus 2, as long as x is not equal to 1, and that's not an issue. And we're taking our limit as x approaches 2 of f of x. And we're going to find that that does not exist, because if we take the limit as x approaches 2 from the left of 1 over x plus 2, we get values that are going to become closer and closer and closer to 0 in the denominator, but from something less than 0. I'm going to indicate it this way, 1 over 0. I'm going to put a little negative symbol right there, because we're going to think about it this way. Something slightly to the left of 2 plus 2 means something that is going to be slightly less than 2, right? It's going to be slightly less than 2. So what's going to happen is that slightly less than 0, pardon me. That makes it a negative number, which means we're tending towards negative infinity. Now you could use a table here to indicate that as well. If we take the limit as x approaches 2 from the right, negative 2, pardon me, from the right, on both of these, 1 over x plus 2. That means that we're taking 1 over something approaching 0, but this time from the positive version, because if you take a number that's slightly greater than negative 2, that is slightly to the right of negative 2, you take negative 1.9, negative 1.99, and so on, and you add 2, you're going to get a number that's slightly greater than 0. Right, so this is actually approaching 0. We say that this would approach positive infinity in this case. In any case, since both of these goes towards positive and negative infinity, we say that this function has an infinite discontinuity.